Let's discuss the wiring and conduit sizing for a 50 kV uninterruptible power supply system. Firstly, we will examine the input requirements. The existing 1-inch conduit contains 3 number 4 conductors. These conductors have an ampacity of 90 amps. The new UPS input requirement is 72 amps, with a maximum of 90 amps. Therefore, the existing conductors and conduit are sufficient for the UPS input. Also, the existing number 8 ground conductor is adequate. Secondly, we will analyze the output side. The existing 2-inch conduit houses 4 1/0 conductors and 1 number 4 ground conductor. This configuration provides an ampacity of 250 amps. The new UPS output is rated at 50 kV amps with a peak current of 218 amps. The existing output wiring and conduit are adequate for a new UPS output. Using 4 number 2 conductors with a number 6 ground conductor would provide an ampacity of 190 amps. This configuration is also sufficient. The existing 225 amp panel is capable of handling the UPS output. To summarize, the existing input wiring, conduit, and ground are sufficient. The existing output wiring, conduit, and ground are also sufficient. The existing panel is capable of handling the UPS output. Based on the information and considering the existing actual load in the UPS system, the proposed wire sizes and conduit sizes are appropriate. However, coordinate the output wire sizing with the UPS manufacturer to ensure compatibility. Ensure any major load additions are cleared with the engineering staff. We'll delve a bit deeper into these points. Firstly, let's discuss ampacity. Ampacity is the current, in amps, that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. This is a critical factor in electrical safety and system performance. The National Electrical Code, or NEC, provides tables that specify the ampacity of various conductors based on their size, insulation type, and installation conditions. It's important to consult these tables to ensure that the conductors selected for a particular application are capable of handling the expected current load. For example, NEC Table 310.15 provides ampacity ratings for conductors rated 0 through 2000 volts. These ratings are based on specific ambient temperatures and installation conditions. Correction factors may need to be applied if the ambient temperature is higher or lower than the table's base temperature. Adjustment factors may also be necessary if multiple current-carrying conductors are installed in the same raceway or cable. These factors reduce the allowable ampacity of the conductors to prevent overheating. Secondly, we will consider conduit fill. Conduit fill refers to the percentage of the internal cross-sectional area of a conduit that is occupied by conductors. The NEC limits the allowable conduit fill to prevent overheating and to ensure that conductors can be easily installed and removed. The allowable conduit fill depends on the type of conduit and the number of conductors it contains. For example, NEC Chapter 9, Table 1 provides the maximum percentage of conduit fill for various types of conduit. If the conduit fill exceeds the allowable limit, the conductors may overheat, and it may be difficult to pull the conductors through the conduit. In this case, the existing 1-inch conduit on the input side and the 2-inch conduit on the output side must be checked to ensure they meet the NEC requirements for conduit fill. Thirdly, let's address voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To calculate voltage drop, you need to know the conductor's resistance, the length of the conductor, and the current flowing through it. The formula for voltage drop is voltage drop equals current times resistance. Conductor resistance is typically expressed in ohms per 1000 feet. The longer the conductor and the higher the current, the greater the voltage drop. To minimize voltage drop, use larger conductors or shorten the length of the conductors. In our scenario, the voltage drop should be calculated for both the input and output conductors to ensure it is within acceptable limits. Fourthly, we must inspect grounding and bonding. Grounding and bonding are critical for electrical safety. Grounding provides a path for fault current to flow back to the source, which allows overcurrent protection devices to trip and clear the fault. Bonding ensures that all metal parts of the electrical system are at the same potential, which reduces the risk of electric shock. The NEC specifies the requirements for grounding and bonding in Article 250. It's important to ensure that the grounding and bonding system is properly installed and maintained. For example, the size of the grounding conductor must be appropriate for the size of the ungrounded conductors. Bonding jumpers must be used to bond metal enclosures and raceways. In this case, the existing number 8 ground conductor on the input side and the number 4 ground conductor on the output side must be checked to ensure they meet the NEC requirements for grounding and bonding. Fifthly, we need to understand overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. These devices interrupt the flow of current when it exceeds a predetermined level. The NEC specifies the requirements for overcurrent protection in Article 240. It's important to select overcurrent protection devices that are properly sized for the conductors and equipment they are protecting. The overcurrent protection device should be rated to interrupt the maximum fault current that could occur at that point in the system. In this case, the existing 225 amp panel on the output side provides overcurrent protection for the UPS output. The panel's circuit breakers or fuses must be properly sized to protect the output conductors and the connected equipment. Sixthly, let's discuss harmonic distortion. Harmonic distortion is a phenomenon that can occur in electrical systems with nonlinear loads, such as UPS systems. Nonlinear loads draw current in a non-sinusoidal manner, which creates harmonic currents that can distort the voltage waveform. Harmonic distortion can cause a variety of problems, including overheating of equipment, malfunction of sensitive electronics, and increased energy consumption. To mitigate harmonic distortion, harmonic filters can be installed. These filters are designed to block or reduce the flow of harmonic currents. The NEC provides some guidance on harmonic distortion in Article 220. It's important to consider harmonic distortion when designing and installing electrical systems with nonlinear loads. In our scenario, the UPS system may generate harmonic distortion, so it's important to assess the potential impact on the electrical system and take appropriate measures to mitigate it if necessary. Seventh, future load considerations are important. While the existing load on the UPS system is currently low, it's important to consider future load additions. The electrical system should be designed to accommodate the maximum potential load, not just the current load. This includes selecting conductors, conduits, and overcurrent protection devices that are sized for the maximum load. It also includes ensuring that the electrical panel has sufficient capacity to handle the additional load. Any major load additions should be cleared with the engineering staff to ensure that the electrical system can handle the increased demand. In this case, the engineering staff should review any proposed load additions to ensure that they do not overload the UPS system or the electrical panel. They should also verify that the existing wiring and conduits are adequate for the increased load. Eighth, let's talk about coordination with the manufacturer. The UPS manufacturer's specifications should always be consulted when selecting wiring and conduit for a UPS system. The manufacturer may have specific requirements for conductor size, conduit type, and grounding. These requirements should be followed to ensure that the UPS system operates safely and reliably. The manufacturer may also provide recommendations for harmonic mitigation and other power quality issues. In this case, it's important to coordinate the output wire sizing with the UPS manufacturer to ensure compatibility. The manufacturer may have specific recommendations for conductor size and insulation type based on the UPS system's output characteristics. Ninth, regarding safety precautions, working with electrical systems can be dangerous. It's important to follow all safety precautions to prevent electric shock and other injuries. This includes energizing circuits before working on them, using proper personal protective equipment, and following lockout/tag-up procedures. Only qualified personnel should perform electrical work. In this case, All electrical work related to the UPS system should be performed by licensed electricians who are familiar with the NEC and other applicable codes and standards. They should also be trained on the specific safety procedures for working with UPS systems. 10th, ensure regular inspections and maintenance. Regular inspections and maintenance are essential for ensuring the continued safe and reliable operation of electrical systems. Inspections should be performed to identify any potential problems, such as loose connections, damaged conductors, or overloaded circuits. Maintenance should be performed to correct any identified problems and to prevent future problems from occurring. The frequency of inspections and maintenance should be based on the manufacturer's recommendations and the specific operating conditions. In this case, the UPS system and the associated wiring and conduit should be inspected and maintained regularly to ensure that they are in good condition and operating properly.